Find the 4-hour unit hydrograph in cubic meters per second per centimeter of excess rainfall. In this problem, stream flow and rainfall data from a given storm are provided in 4-hour increments. The watershed area and base flow rate are also provided. Possible answers A, B, C, and D are shown on the right in units of meters cubed per second per centimeter of excess rainfall. Before developing the hydrograph, we'll first need to account for the base flow. The base flow rate in the stream plus the excess stream flow caused by the rainstorm equals the total recorded stream flow. To develop the hydrograph, we're interested in the stream flow generated by the storm only. Therefore, we can subtract the base flow from the measured stream flow to determine the stream flow data from the storm only. Graphically, we can plot out the total stream flow data from the given dataset, then plot the constant base flow as a negative value, shown in orange, and the storm stream flow equals the stream flow less the magnitude of the base flow for all 10 measurements. To calculate the stream flow from just the storm, we can simply subtract 14 from the total flow rate. Also, before developing the hydrograph, the infiltration of rainfall in the soil must be accounted for. The infiltration rate in centimeters for a 4-hour time period equals the total infiltration in centimeters divided by the storm duration in 4-hour time increments. For this problem, we'll assume a constant infiltration rate, so we'll use the capital delta notation. We'll first determine the total infiltration, delta F, which equals the total rainfall depth minus the total depth from runoff. The total rainfall depth is the sum of the individual rainfall entries, which equals 9.6 centimeters. The depth of runoff equals the volume of runoff divided by the watershed area, where the volume of runoff equals the sum of the flow rates times the time step, delta T. The sum of the flow rates equals 694.4 meters cubed per second, and the time step is 4 hours. The area of the watershed is 180 kilometers squared, and after a few conversions are made, the runoff depth computes to 5.56 centimeters. Therefore, the total infiltration, delta F, equals 4.04 centimeters. Since the rainfall lasts 16 hours of measurement, the storm duration is 4 4-hour time periods, which makes the infiltration rate, F, equal to 1.01 centimeters every 4 hours, which we will round to 1.0 centimeters every 4 hours. Similar to the stream flow, the depth used to develop the unit hydrograph should only be the rainfall which becomes runoff, which we'll call the runoff depth. Graphically, the rain, infiltration, and runoff depth would plot as shown, and the runoff depth would calculate to 1 centimeter less than the recorded rainfall for each of the 4 time periods. At this point, we can start calculating the unit hydrograph. For sake of convenience, let's designate the storm flows with Q sub n and the runoff depth with P sub m. And the goal is to solve for the unit hydrograph ordinate, U sub n minus m plus 1, as defined in the discrete convolution equation. We set up the hydrograph so it reads similar to our convolution equation, where the storm flow equals the sum of the product of the runoff depths times the unit hydrograph ordinates. The variable n represents the time periods, and the variable m represents the quantity of flow each single hour of rainfall contributes to the total runoff, where the four columns equal m's 1 through 4. Beginning at the first row, since n equals 1, the second, third, and fourth terms are 0, since the rainfall has not yet begun for those time periods. From our data table, we recall the runoff depth for this first 4 hours is 0.2 centimeters. Therefore, 0.8 meters cubed per second equals 0.2 centimeters times u sub 1. In solving for u sub 1, it equals 4 meters cubed per second of runoff per centimeter of excess rainfall. The second time period is solved the same way, but this time the first 2 hours of runoff contribute to the stream flow because n equals 2. Solving the convolution equation for the second ordinate and plugging in the first ordinate, u sub 1, u sub 2 equals 8 meters cubed per second per centimeter of excess rainfall. For the third time period, we can solve for u sub 3 by writing out the convolution equation, plugging in u sub 1 and u sub 2, and we calculate this third unit ordinate as 18 meters cubed per second per centimeter of excess rainfall. If we continue this process for the entire hydrograph, we can complete the table and solve for all unit hydrograph ordinate values. When reviewing the possible solutions, the answer is D.